In this lecture, we'll model this electro-osmotic flow. So this is the situation that we are going to consider. So we'll consider electro-osmotic flow over a flat surface that is kept in an semi-infinite media of electrolyte containing positive and negative charges. So we have this flat surface with negative charge, and that leads to a zeta potential at the surface, and we assume that the zeta potential is uniform along the x direction or the axial direction. And at the wall we have the no slip boundary condition, and far from the wall we have that the potential, the equilibrium potential, which is formed only due to this ideal formation, tends to 0, and the gradients in velocity also tend to 0 as z tends to infinity. So we'll model the electroosmotic flow, which I'll also call as EOF, over this flat surface. Now to model this, we'll assume that the Reynolds number is significantly smaller than 1. That is, we are working in the Stokes flow regime. And this is a reasonable assumption. Once we calculate the typical velocities in electroosmotic flow, we'll see that Stokes flow is a reasonable assumption for electroosmotic flow in microchannels. So for Stokes flow, the governing equation is so we have this pressure gradient term, the viscous terms, and in addition we have this electric body force term, where the free charge in the ideal couples with the electric field. The electric field is given by the negative of the gradient in potential phi. Now in this case we have potential due to two effects. One is the external electric field, and another is the potential equilibrium potential established due to the formation of electrical double layers. So we'll say that phi is composed of minus E naught x, because we are applying an electric field E naught in the x direction, plus the equilibrium potential which results due to the formation of electrical double layer. So if we set E naught to 0, we'll get back the situation where we just have an ideal and no external electric field. And the charge density rho f is given by the Poisson equation, which is minus epsilon del squared phi, and in our case this becomes minus epsilon del squared phi equilibrium. Now because our problem is all the variables are uniform along the x direction, so the only variation in the equilibrium potential is in the vertical direction, in the z direction. So this can be written as minus epsilon d squared phi equilibrium over dz squared. So a final equation, so this equation can be simplified as Okay, so where the electric field is can be decomposed into the external electric field and the electric field due to the equilibrium potential in the EDL. Actually, this term has only the Z component because the equilibrium potential varies only in the Z direction. And recall that we have already solved for this equilibrium potential. So for the case when ZE zeta over KT is significantly small, equilibrium potential is given by this relation. But in our analysis we don't make the use of this assumption. Our analysis is valid for all zeta potentials. Now next what we'll do is that we'll simplify this equation and try to solve it. So let's look at the X component of this governing equation. So the X component is given by 0 equals to minus del P by del X plus eta, which is the viscosity, and note that there is no variation in the X direction, so we'll just have del squared U over del Z squared minus epsilon d squared phi equilibrium over dz squared, and the electric field in the X direction has only one contribution due to the external electric field, that is E naught. So this is the governing equation that we want to solve with the boundary conditions that U at the surface is 0 due to the no slip boundary condition, and as Z tends to infinity there is no gradient in the velocity. Next we note that we are not applying any external pressure gradient, and the zeta potential and all variables are uniform along the X direction, so we don't have any pressure gradient actually in the X direction. So this equation further simplifies to the balance of the viscous terms and the electric body force only. And note that there is no V component or the vertical component of velocity, there is only X component of velocity. So U, the velocity, has only the X component. So the flow is actually parallel. Now we'll solve this equation to obtain a relation for electro-osmotic flow in terms of the electric field. So if we integrate this equation once, we'll get viscosity times the velocity gradient is equal to epsilon. So electric field, externally applied electric field, is constant, so E naught is a constant, and we get d phi equilibrium by dz plus an integration constant. But we note that as z tends to infinity, du by dz tends to 0, and d phi by dz also is 0. Therefore the equilibrium constant must the integration constant must be 0. Next we'll integrate this equation again, and we'll get eta times u at any value of z minus u at z equals to 0 is epsilon times E naught phi equilibrium at some value of z minus phi equilibrium at z equals to 0. And now recall that at z equals to 0, phi equilibrium is actually the zeta potential. So, and another thing is that at z equals to 0, we have the no-slip boundary condition. So this u at z equals to 0 is 0. So simplifying this relation, we get the solution to this problem, and that is given by epsilon E naught over eta, which is the viscosity, is times phi equilibrium, which is a function of z, minus the zeta potential. So this is the solution for electro-osmotic flow over a flat, infinitely long flat parallel plate with uniform zeta potential. Now note that to derive this equation, we have not made any assumption on the magnitude of zeta potential, that is, and this relation is equally valid when zeta potential is small or it's large. That means we haven't made any, we have not solved this only for the Debye-Huckel limit. It is a general solution. So from this equation, we can note that as z tends to infinity, that is, you go significantly far from the surface or outside the electrical double layer, the potential, equilibrium potential, is 0. So the flow velocity outside the electrical double layer is given by minus epsilon zeta over eta times E naught. So this is the velocity that is attained by the fluid outside the electrical double layer, and again this is true for any limit of the zeta potential. So that means we have not restricted ourselves to low zeta potentials. But just to plot this expression for the velocity profile, we'll now make the assumption that z e zeta over kt is significantly small compared with 1, and this is the Debye-Huckel limit. In that limit, we already know that phi equilibrium is given by zeta times e to power minus z over lambda d, where lambda d is the thickness of the electrical double layer. Now if you plug in this expression into this velocity, the solution for velocity profile, so we have u is minus epsilon zeta E naught over eta times 1 minus e to power minus z over lambda d. So if we try to plot this solution on the same curve, so at z equals to, on this same plot, at z equals to 0, we have the no-slip boundary condition, and as you move further from the surface and the flow velocity approaches this this magnitude of minus epsilon zeta eta over eta times E naught. So this is the velocity profile within the ideal, and outside the ideal over here the velocity is minus epsilon zeta over eta times the applied electric field. Now we note that for most of the practical cases the ideal is actually very thin. So we know that ideal thickness is order 10 nanometers or even smaller. So for microfluidic applications, this velocity profile is something that you actually do not care about and you don't see. So because we have a channel which has a thickness of order 10 micrometers or larger, and this gradient in velocity near the surface occurs in the region of thickness of order lambda d, that is the ideal thickness, and that is about 10 nanometers. So on this scale of the thickness of the channel, the flow actually appears to slip on the wall because this region is very thin near the walls. So what you actually see is that the flow apparently slips on the wall with the slip velocity of u is minus epsilon zeta over eta times E naught. And this slip velocity is called the Helmholtz-Smoluchowski velocity. So for most practical microfluidic systems, the effect of wall charge and applied electric field parallel to that wall is that we have this slip velocity at the walls, and that's due to this electro-osmotic flow, and this slip velocity at the walls is proportional to the electric field, and the proportionality constant is this quantity, which is also called as the EOF mobility. So if you now here we have looked at the case of a single flat plate, but if you look at a microfluidic channel, let's say a two-dimensional channel where we have these two flat plates and there's an EDL which is really thin next to these charged walls, and you apply an external electric field, it would appear that the flow is slipping at the walls with this velocity, and because the flow is slipping at the walls, we'll get a plug flow profile with no gradient in velocity, and throughout the depth of the channel the velocity would be given by this particular relation. And this is the case when there is no pressure gradient, or there is no the zeta potential is uniform, that is there is no gradient in zeta potential along the axial direction. Now what's interesting is that unlike pressure driven flow, which depends upon the dimensions of the channel, the electro-osmotic flow does not have the channel dimensions does not depend upon the channel dimensions. That means, as we have seen for pressure driven flow, when you reduce the thickness of the channel, the size of the channel, the hydraulic resistance increases, and therefore you need higher pressure to pump in the liquid. But in electro-osmotic flow that is not the case, so the flow velocity is actually not depending upon the channel dimensions. So therefore for microfluidic systems, electro-osmotic flow is often more convenient than pressure driven flow, because the effects of higher hydraulic resistance do not come into picture for electro-osmotic flow. Now we can look at a typical velocity magnitudes of electro-osmotic flow. So the typical zeta potential is of order 100 millivolts, and we have a negative sign because we are looking at a negatively charged surface. The viscosity is about 10 to the power minus 3 in SI units, and the permittivity is 80 times 8.854 into 10 to the power minus 12 farad per meter, and this is for water. So if you plug this relation into this, plug these values into this relation, we'll see that the electro-osmotic mobility is about 7 into 10 to the power minus 8 meter squared over volt second. Now this is the mobility. So if you apply an electric field, and the typical electric field in microfluidic devices that you can apply is about 10 kilovolts per meter, so that is about 10 to the power 4, that is 10 to the power 4 volts over meter. So the velocity, the EOF velocity that you would get is the EOF mobility times the electric field, and that is 7 into 10 to the power minus 8 times 10 to the power 4 meters per second, and this is about 0.7 millimeters per second, or in other words, typical EOF velocity is about 100 micrometers per second to 1 millimeters per second. So this is the typical EOF velocity magnitudes. And also note that this EOF mobility has a similar magnitude than the electrophoretic mobility of small ions. So when we look at electrophoresis, we will see that the combination of electro-osmotic flow can also modify the migration characteristics of charged ions, because the flow velocity, the electro-osmotic flow velocity is also of comparable magnitude comparable magnitude to the electrophoretic mobility of the ions, that is the speed of ions when an electric field as they migrate through an electrolyte solution under the effect of an applied electric field.